yourselves, why did I ask you to look at GPS and GIS? And the answer is, well, because you guys are studying
Technology,
cybersecurity,
cybersecurity.
and if the guy in Colorado t-shirt would actually say that, then we could proceed. But having said that, it is a real pleasure for me. Babs has been a vice chancellor on the Boulder campus. She's been in Washington, National Science Foundation, other kinds of things. And so please welcome her, and thank you very much for coming. You may want to, because this is being recorded, there is a microphone here. I don't know how to put this on because I have no technical abilities.
I'm going to talk about information security when we get there, rather than necessarily cyber security.
Oh, God.
Yep. So you have contact. Okay, very good.
Okay, good. Okay. But let's start with what's GIScience anyway. GIScience develops theories and methods and tools and data and technology to manage geography, places, things on the surface of the earth or near the surface of the earth, processes, essentially answering three big questions: where and what and how come. And our job as GI scientists, now I'm speaking for myself and my colleagues, not just in geography but in other disciplines cognate to that, we characterize natural and social and societal contexts to understand the where and the what, and hopefully the why too. GIScience is by nature interdisciplinary. I do work with computer scientists, I do work with geologists, I do work with information scientists, I do work with environmental engineers. I am a data modeler, I work with process modelers. There is a huge coupling, a very strong linkage between technology and policy, and a little bit of security too. We talk about it in terms of ethics, but I'm going to talk to you about it in terms of security today, because of especially recent developments. But let me start by talking to you a little bit about geoscience and geospatial data. Who cares about geoscience? Of course I care, I am one. But if you think about humanity, human populations have reached a level that our resources are becoming limited and compromised. I mean, it's a truism. I don't think I even need to say that. But if you think about the first 100,000 years of human existence, there were really very few impacts on the planet. And in the last 300 years, we have altered the planet perhaps irreparably, maybe for the better, but irreparably. GIScience can improve the quality of life, and it can help to conserve the planet. It's not the only discipline that can do so, but it's certainly one of our goals. And we think a lot about the landscape and the planet and how to conserve these resources. So we use GIScience to detect and address problems, to provide crucial information, to identify the source and the location and the extent of these impacts, and then we help decision makers to devise plans to monitor resources and so on and so forth. Now, Jim asked me to distinguish between GPS and GIScience, so this one slide is for you, Jim. GIS is not GPS, it's not GNSS. It is an umbrella term, or rather I should say the umbrella term is geospatial analysis. GIScience, GPS, remote sensing, cartography, they're all within that umbrella. So we use GPS, you probably will use it as well, but it is not specifically what we do. Let me also talk to you a little bit about the difference between spatial data and geospatial data, because it matters. Spatial data, architectural blueprints, X-rays, CAT scans, medical imagery, full text documents, anecdotal documents, handwritten diaries, some photographs. Those are spatial data. And they are different from geospatial data because geospatial data is georeferenced. It has some coordinate system that will allow you to do two things. The georeferencing allows you to tie at least one of your data sets back to the planet. So usually that's in latitude and longitude, but there are a lot of other coordinate systems that we use as well. The other thing that differentiates spatial from geospatial data is that geospatial data is spatially referenced. That is, we can register one data set with another, and that allows us to do overlays and data integration and data harmonization. So things like maps and imagery can be thought of as geospatial data. And at the top here, I'm showing you an example of just a photograph that a planner might use along with building footprints, just to show you that we use them for data integration. So georeferencing and spatial registration are really what differentiates that architectural blueprint, that X-ray, from maps and satellite imagery. One might also ask, why is spatial data so special? It's not special, actually. It's tricky. It's tricky to work with, and you have to apply somewhat different methods to data that is georeferenced. And there's three aspects of that. The first is spatial dependence. I'm going to talk about each one in some detail. The second is scale dependence, and the third is statistical heteroscedasticity. And now I have to ask you, because I've never spoken to you before, what's your level of statistics? Do you know what heteroscedasticity is? Okay. Heteroscedasticity means that if I have a study area, here's a study area, and I'm measuring the variance of the area as an entirety, I get a number. But I may find that those, the variance values locally actually show quite a different variation, and that the global summary does not represent all of the locales. So heteroscedasticity, the cedasticity is like standard deviations, and the hetero means they change. So let me talk about all three, and I'll come back to the heteroscedasticity in a bit. We'll start with spatial dependence. Spatial dependence literally means that there are some variables that if I know the value right here, I can make a really good guess right here or right here. But if I want to make a guess over there, it gets harder. And if I want to make a guess over in Fort Collins, it gets even harder. So spatial dependence means that things that are closer together are more similar than things that are farther apart. And this is Tobler's first law of geography, one of the few laws that my discipline has. But what the spatial dependence does to you as an analyst is it means that because your proximal spatial observations, the value here and the value here being very similar, you cannot assume independent random sampling when you do statistical inference. You cannot assume if you sample a digital elevation model or population density by census tract that the population density here is going to be independent of the population density here or here. That's spatial dependence. So we have to have special methods that measure that, quantify it, and work with it. So if we're working with the examples I showed you, if I know the value here, what's the value here? I'm within the same data layer, the same data set. And I work with what's called spatial autocorrelation. Can I correlate the values that are at some small lag distance from a value that I've sampled that I know? That's autocorrelation within your data set. There's also spatial correlation, which means that if I know the income in a census tract, if I know the education level in a census tract, I can make a pretty good guess of the income because education and income are highly correlated. So these are two parts of it. Values of variables at nearby locations tend to be similar, so we can't use regular conventional statistical methods. So that's spatial dependence. Then there's scale dependence, and scale dependence makes spatial data special because the content, the geometry, and the appearance of geographic information on all geospatial data, in fact, is different depending on how closely you look at it. You can think of that as how close you are to the surface of the Earth. You can think of it as the units of measurement that you use to measure something, length or area or whatever. So if you want to work with scale dependence, you are working with two problems that are pretty big in geography. One is MOP, the modifiable areal unit problem, and the other is the ecological fallacy. But basically, statistical summaries and aggregations are going to vary if you change your units of measurement. So if I measure how long is the coast of Britain, it's a very famous article by the guy who invented fractal geometry, Ben Mandelbrot. If I measure the length of the coastline using segments that are this long, I'm going to get a length here, 2,400 kilometers. But if I use smaller units of measurement, in this case 50 kilometers, I get a bigger length. And I could take it all the way down to walking around the coastline. And it will continue to increase without limit. This is one of the things that Mandelbrot demonstrated. This example here has to do with how we regionalize space, how we aggregate things, and it's the ecological fallacy, which says that you should not draw conclusions about individuals based on aggregated data. So if we have 3 flu cases, flu, that's it. Everybody's got the flu these days. If we regionalize this space so that this person has the flu and this doesn't, we could also regionalize it this way, and we would get a different statistical summary, that this region is flu-free and this one is flu-prone. Or we could work this way and get an illness rate of 50% and so on and so forth. So the units of measurement we use, scale dependence, is one thing, and the configurations with which we aggregate things like counties or voter precincts or watersheds, all sorts of things, will impact the way we measure data, and that has to do with scale dependence. Now, I'll just tell you this because there was a point in time where I was a graduate student, prehistoric times, but nonetheless, and the first time I saw this, I thought, oh, come on, that's crazy. Well, I was wrong, and it turned into my dissertation. So here's my dissertation in one slide. It's probably about what it's worth. I did exactly the same thing, except with not using the coast of Britain. I used 4 different areas that have different geomorphologies. A fjord in British Columbia that is a submergent, drowned valleys. A place near Sioux Falls, South Dakota, where you have the incision of rivers over consistent bedrock. A portion of Hudson Bay, called Hudby in my file names, that is an emergent geomorphology. It's caused by the uplifting of continental plates when glacial ice recedes. So the plates kind of bound up, isostatic rebound. And this is down near Brownsville, Texas. It's a depositional barrier. And I measured them at different resolutions, and I found that sure enough, if I ran a regression, I found out that each of these is actually not only changing the length as you change the units of measurement, but it is also impacted by the different geomorphology. So some places, like the Sioux River, is changing very slowly. It's got a flat slope. But the fjord and Hudson Bay, they have a steeper slope, so they are gaining detail more quickly as I use smaller units of measurement. And indeed, Texas, it's not a line at all. It's a polygon because it's a space-filling curve. It's actually bending back on itself so fast that if Euclid were thinking about it, Euclid would probably treat it as a polygon as opposed to a line. So scale dependence is a really big deal. And then this third problem, the statistical heteroscedasticity. The best example that I could think of is climate change and global warming, which isn't, because if you look around the United States these days, this is from yesterday, I think, and the current temperatures are pretty cold, and so a lot of people are saying, well, there can't possibly be global warming. Look at how cold it is. But if you look at the trends, you'll see that the 5-year average and the annual average since 1880 going up to 2000 is clearly warming, and there are parts of the world, the local data sets that are quite different than other local parts of the world. In fact, Australia, and you can see from this animation, Australia is in fact displaying much warmer temperatures than it should. So what global warming is actually doing is it's giving us more and more extreme weather events, more and more extreme temperatures. And it's rather a misnomer to call it global warming. It's global climate change. But the fact of the matter is, if we look at the variance for the globe as a whole, as opposed to the variance for any locale, we will get different values. And that's what the heteroscedasticity is. There are ways to deal with heteroscedasticity and scale dependence and spatial dependence, all of these. This is one method that's used to deal with the global versus the local summaries. This is taken from a study in Columbus, Ohio. I had nothing to do with it. Luke Anslin, a very famous geoscientist, looked at places. He was looking at census tracts, and the red census tracts are places where there is high crime that has high crime adjacent to it. The blue places are places that have low crime, where low crime or medium crime is adjacent to it. So you can think of hot spots and cold spots. And he used some statistical methods, Moran's eye, but a local version of that, to not only look at this in a statistical manner and a geographical manner, but also to look at the statistical significance of this. And you can see there's a lot of other methods that you can use. His is called LISA, for local indicators of spatial association. But you could also use weighted least squares and a lot of other Minke's method, Rouse-Minke method. And I'm not going to dig into those. I just want to give you a flavor for the fact that we know we have these problems with spatial data, and we have been developing methods to work with them. So this is GIScience. Now you know everything there is to know about GIScience, and you know everything there is to know about why spatial data is special. So let's get on to the policy and the technology and the security. Okay, policy. I'm not a wonk. I'm not a policy wonk. I'm a scientist by training, but I do work with a lot of people who do work with policy. And if you talk to someone in Washington, D.C., they will tell you that policy is exactly this. It requires the projection of knowledge in a spatial context. And what that means in simple English is, what are the implications of this particular, today's spatial process in this place? So when we talk about GIScience and policy, we're talking about urban planning, we're talking about SDSS, spatial decision support systems. We might talk about political districting, might talk about flood maps. And I'm going to talk about two of these examples, both of them pretty close to home. The Boulder 2013 floods. How did your house fare?
It flooded 2 feet.
Yeah, we were right within, my husband's a retired plumber. We have a lot of friends in the trade. We were right below the electricity that would have wiped out the house. But we lost our furnace and our freezer and our washing machine and our dryer and the floors and the walls in the basement. We lost it all. A lot of people did. This was an 8-day rainfall total of 17.5 or 17.15 inches, and our average precipitation in Boulder is usually about 20 inches. So we got almost the year's supply of rain in 8 days. It was amazing to watch this happen. You can see the damage of homes destroyed and or damaged, 1,800 people evacuated, 150 miles of road damaged, and probably the estimates are about $150 million just to fix the roads. Just to fix the roads. There's some policy issues here. This is I pulled this off the web. In our driest years, you can see we get 6 or 7 inches of rain. In our wettest years, we get a lot, close to 30 inches in really wet years, but mostly it's about 20. So in this particular year, on September 10th, we were at about 12 inches, and 3 days, 5 days, 8 days later, we had hit one of the wettest years on record. Yeah, it was pretty incredible. So what Boulder has done, we're talking about floods and policy here, is they have initiated a program called CHAMP, which is the Colorado Hazard Mapping Program. It's still going on. And as I go through all of these examples, I'm going to talk to you about what kind of GIS data is used and possibly what kind of modeling methods. So to work on remapping the floodplain, you need to know where the water went. This is a Google Earth image from 2015 with the water overlaid. There's another example of that spatial registration. And here's a revised flood map for showing data from FEMA and Boulder County. Both of the models are being incorporated here. We use terrain, we use soils, vegetation, road networks, population density, land value, geology, the hydrography, meaning the streams and the catchment ponds and the ditches and the reservoir, and then the kind of modeling that someone would do to work on this would be to develop metrics of topographic wetness. How much water can the soil take at different places? What's the depth to bedrock? How fast does the soil absorb water? What is the water flow direction and what's the water flow accumulation as you move downhill from the mountains? What is the hydro capacity of the area? So all of a sudden, when I bought my house, not all of a sudden, when I bought my house, I was in the 500-year floodplain, and all of a sudden, I'm being told I have to have flood insurance. I'm glad. I don't want to have to replace my furnace again. Here's another example, political redistricting. Why do we redistrict? The census counts all the people up every 10 years. It's called the decennial census, and the primary purpose of it is to update voting districts, federal voting districts, but also state and local, but the federal ones to reflect changes in population. And that is for purposes of representation in Congress and for the Electoral College to elect senators and congresspeople and the president. The redistricting also affects the provision of resources from the federal government. Food, breakfasts and lunch for low-income children, health care, Medicaid, Medicare, Indian health services, a lot of different programs. And so it really matters when they redistrict because they're trying to redistrict, in theory at least, to draw the voting boundaries so that each boundary gives a representative mix of all parties, all ethnicities, and so on and so forth. Now, gerrymandering is what many politicians and policy people are saying is going on now, which is redrawing boundaries to gain political advantage. So I'll just show you some of these, and a lot of websites are starting to say the redistricting that happened for the 2016 presidential election is all wrong and I've got a better solution. This is what the count is for House of Representatives and the Electoral College by different state for 2000. So remember, you count people up only once every 10 years. And this is just one website. I'll show you gerrymandering, which is when you redistrict, you want to have a geometry that has a particular shape, which is as compact as possible. So this is the existing congressional redistricting, and you can see here's a voting district. And the reason it's called gerrymandering, there's some historical politician whose name was Jerry something, but the mander is from salamander, like a, creepy long thing, yeah, okay. And so you can see that some of these districts are really stretched out and odd shapes, and this is somebody who's just all about compactness. And I don't know that this is necessarily right or wrong, but at least this person is saying we could have different voting districts that would have different kinds of political mixes, and we might find that we have different representation and different sets of resources going to people. Here's Texas, a little bit better. This is the existing, not so much gerrymandering, a little bit here and there, but not too much. And then this is this person's solution. So these are just two examples, the flood mapping policy work and the redistricting, where GIScience has an impact. On to technology. Okay. So the technology piece is where GI scientists utilize geospatial data and technologies to solve problems. There's two kinds of work that GI scientists do. There is applied GI science, or GIS applications, and there's theoretical GI science. Most people think of GI science in terms of the applications, and I'm going to give you some examples of those. But basically, you're using existing methods to study some application. You're not trying to change GI science. You're trying to make a difference in the understanding of some process or phenomenon on the planet. Theoretical science is to advance GI science itself, to change the way we do GI science. So I'll talk mostly about the applied examples, and I'll talk to you about some work that's going on in my lab, the Meridian lab. I'm doing some of it with my students. Stefan Leik is doing some of it with his students. Here's one application delineating urban fire risk in Boulder, Colorado, and working with what is called the WUI, the Wildland Urban Interface. So the issue is to look at areas in or near the edge of town that are at high risk for wildfire and to model how to mediate the risk of wildland fires, cutting down trees, moving a lot of brush away and clearing ground. But there is ongoing work to actually delineate the WUI boundary, because what happens at the WUI boundary is the U.S. Forest Service and the USGS fire teams and local fire teams, they put all their attention into working right at that urban wildland interface. So there's actually two parts to the WUI. There's the intermix and the interface, but they're both around the boundary. And let's just talk about what the existing situation is and then the work that's going on. The big honchos of WUI delineation are in Wisconsin at the Silvis Lab, and this is their solution for Boulder, Colorado, and it's based on census data aggregated to a block level. Remember the MOP problem and the ecological fallacy and how you aggregate data? Well, what our lab is doing is saying we don't want to work at an aggregated level. We want to go down to individual buildings, and we want to redelineate the WUI and see how different is the solution from the folks at Wisconsin. Yeah. So here's their solution. Without going in too much detail, I'm trying to give you a flavor rather than to do deep dives or surgical strikes. This is the Wisconsin solution by Blockface for Boulder County. And you can see the intermix and the interface, but the shaded areas are areas that are at high wildland fire risk. And you can see the differences when you generate the same model using the same methods. They publish everything except starting from building footprints. You can see that the wildland fire risk extends well into the city. There are several areas up in the Montane region, because remember this is up towards the Continental Divide, that the Wisconsin crowd designates as high wildland fire risk that our model does not, and we're still working on it and building it up. At any rate, we're trying to find out how much the answer changes when you disaggregate data and change the precision with which you measure it. Here's another example. I'm working on this one with my senior doctoral student. We're citing an anaerobic digester hypothetically. It's a big compost bin, industrial strength, 60 meters tall, big compost bin. And the idea is to try to look into the potential for adopting renewable energy based on the fact that there's a lot of farm waste and crop waste, particularly in all parts of rural America. So the idea of the anaerobic digestion is that you put in all of the crop waste and the manure and so on and so forth, and you have little creatures that mix in here and create sludge and fluid, and eventually you get biogas, and then you take the fluid and you ship it back to the farms, and it makes really nice organic fertilizer. So you're actually recycling things and doing it well. But I mean, I don't think I'd want one of those in my backyard, and I certainly wouldn't want one on Pearl Street Mall. Neither would anybody else. So where do you put the thing if you're going to do it? And this is one of the reasons that the United States has not adopted anaerobic digestion and renewable energy. This is kind of the process. You've got biodegradable waste. It goes into the big can, and it creates gas that goes to the power plant eventually and generates electricity without any coal, which is sort of the idea. And then the fluid, the effluent, goes back to the farm. So what we're doing with the doctoral project has to do with data availability. The USDA produces, I have to go to another slide here. Nope, maybe not. Well, we'll leave it here. The USDA distributes data on farms. It will tell you. Boulder County has 187 farms, but it won't tell you where they are. it only says there's 187 in the county, and 45 of them are 2,000 acres or more, and 15 of them are 10 acres or more, and so on and so forth. They're stratified, and it's at the county level. This is a problem in public health data as well. And so what we're trying to do is to figure out if we can generate maps that would tell us where would be an efficient or an equitable place to put the anaerobic digester, knowing only that there's 187 farms and some of them are big and some of them are small. So we're using Monte Carlo simulation, we're using decision trees and machine learning to try and randomly situate farms in places that we know many, many, many times, build up a frequency distribution of the farms. So we're using land use data, and we have Boulder parcel data. That's why we're working in Boulder County. So we have the truth over there somewhere. We're not using that. We're using our Monte Carlo simulation to come up with stochastic models to figure out good places. And once we have those, then we're going to check it against the real data and see how well we did. And if we can solve this problem for Boulder County, where we know the truth, the parcel data, then we could go to other places in Michigan or Wisconsin or Nebraska or Texas, where the parcel data might not be available, and solve the problem for them. So here we have farm agricultural parcels for the whole county. This is a portion of the county, and we can actually look at which of these parcels are truck farming that goes to the Boulder market, public market, and which are the really larger places. And in terms of equity and efficiency, anytime you cite something, if you cite a facility like a school or a hospital for efficiency, you minimize the travel of anybody from any direction. If you do it for equity, you minimize the travel for the person who lives farthest away. So we want to solve both of these problems, so we put this anaerobic digester, since we can't put it on Pearl Street, we're going to start by putting it at the Valmont power plant, because they're already generating power, and if you do that, then you don't have to truck the gas over to the power plant. It saves a little bit. So here's a solution to locate it at the power plant, and this is 50 runs, not 1,000 runs for our actual bootstrapping or a Monte Carlo simulation, and we're pretty close to a normal distribution about how far you would have to travel from these farms that you situate 1,000 times. This is the farm that would be closest to the Valmont power plant, and this is the one that would be farthest away on average in our solution. And then we said, well, what if we don't put it at the power plant? So we're working on that. Yep, this is it. And so we have criteria here. The ideal candidate location that's not at the power plant is one of the larger acre farm clusters, bigger than 1,000 acres, in a cultivated farm land use polygon, and has a route less than 14 kilometers to the Valmont power plant. And so we're finding that these are the two places in the county that meet all of those criteria and fall within that Monte Carlo simulation. So in this solution, people would take their bio-waste and their crop waste and their manure here. It would be turned into biogas, shipped to the Valmont plant, and then once the liquid effluent is there, it would go back to all the farms. So we're working on this and trying to refine this solution. One of the ways that we're trying to refine the solution is that we realize that Boulder isn't flat. So the distance from me to Jim is whatever distance it is, a couple of feet. The distance from me to the back of the room, if I measure it as just horizontal, assuming that we all live on a tabletop in the Euclidean plane, I'm going to be wrong in my distance estimation. Now, if you think about what goes on in Boulder County from west to east, it's really flat and then it gets really hilly. So if we're measuring our distances here in Euclidean space, we're going to have a problem when we think about what's the closest place for efficiency and equity. So this is some work that I've been doing with another student that I'm going to incorporate into this work with this doctoral student, which has to do with surface-adjusted terrain metrics. This is what reality actually looks like. You know, it's highs and lows, and terrain gets rough and non-uniform. And here's the difference between the horizontal distance from point A to point B and the slope included distance. So we've been working, this is theoretical GIS, not applied GIS, to figure out ways to incorporate slope-adjusted distances and areas and elevation estimates into our other models. So the planar distance is just taking a DEM and assuming every pixel is flat and it's uniform and there's no bumps and no hills and valleys and so forth as the crow flies. And we're trying to change it to distance and surface area as the horse runs, so on and so forth. And so very briefly, here are our study areas. We tried to pick 6 places around the country. Some of them are very flat, like Louisiana. Some of them are very mountainous, like Colorado and Washington. And then what we did for each one, this is North Carolina, we put 1,000 random transects on it and registered those. There's the spatial registration at 4 different resolutions. And then we started measuring distances on these, checking them against LiDAR data, which we know to be pretty precise and pretty accurate. And what we found was when we compared the distance on these 1,000 transects that we randomly place on these 4, is that the RMSEs, that is the root mean square error, that is the squared positive error difference between our estimates off the random transects and the LiDAR data. If we're in hilly terrain or rough terrain, for at coarser resolutions, we've got more error. So, I went backwards. So here's an example for measuring distance. This is as the crow flies. Here's several different ways to measure it as the horse runs. And we found that there were methods that work better at 10-meter resolution and different methods that work better at 100 or kilometer resolution. That's great for measuring distance. And we thought, oh, problem solved. Well, we don't have to work for surface area or elevation. We use the same methods, right? Wrong. So surface area and elevation and distance are 3 different tasks. So in addition to working with terrain and the interpolation method, we've also got this task. And then we have to think, do you want the most precise, accurate answer? Do you want to process this as quickly as possible? Are you doing it on your cell phone? Are you in the middle of a wildland fire and your boots are on fire? Or do you want to have a balance? And you can see, use a bicubic interpolator or a linear interpolator. It doesn't matter. Use weighted average, depending on what's your task. So this is the kind of work we're doing, and we're incorporating that into the anaerobic digestion model as a first pass of trying to see whether this more accurate estimate of distance works. And on to security. I'm keeping my eye on the time here. I have to tell you about security. I have worked with security, and I'm going to end with an example of it, but mostly when GI scientists talk about security, we think about the ethics of what we're doing. Are we using this data for a good reason, for improving the quality of life, for preserving the planet? And there are a lot of companies that are. I'm sure everybody knows what these images are of the Google truck. There are a lot of things about what Google is doing, mapping every place on the earth, that are good. And there are a lot of things that aren't good. So I had my cell phone, this was a few years ago, and I was walking by the Starbucks on Broadway up by main campus. And just as I walked by the Starbucks, I got an ad for a Frappuccino. And it really scared me. It was spooky. I mean, literally, I was walking along and ding, it's like, no. And I turned off the GPS in my phone right away. I don't want you to know where I am. It's none of your business. But other people who get lost in box canyons in Utah might very well want somebody to know where they are. So there's 2 edges to this particular knife. Matthew Honan had a great article in Wired magazine. The article is called something like, Where Am I? And he ran this experiment for some weeks. He just constantly ran every location app he could on his cell phone and just watched what happened. And his friends knew where he was at every moment, and all the corporations and companies and a lot of different organizations knew where he was. So the pros that he concluded were that he was able to meet friends, he was able to explore new restaurants that he hadn't thought of, compare gas prices, it was great. But the cons were that he gave up a lot of his personal security. And he also was spending an awful lot of time, and I don't even have my cell phone with me, see, I just keep it away from me. He was like this, And like, here's reality. Here you all are. It'd be like me giving a talk and talking to my cell phone. So that detachment from reality is really part of this security issue. And we can take it farther. We can take privacy and surveillance into this notion of what goes on in the global south, where developing regions may actually lack the technological knowledge. And as they develop, in this case, agriculture, as they develop other kinds of resources, mineral resources, industrial resources, and so forth, they may not be cognizant, the workers may not be cognizant of the extent to which technology and information privacy and anonymity and location-based services are actually draining them of their freedoms and so forth. So there are downsides to this, and there are good sides to this too for resource location. I don't want you to think this is all dark, and I tend to lean that way, but that doesn't mean that there aren't good things about it, and I will give you an example in the very end that is what I think of as positive. Here's an unintended consequence. In January 2018, the fitness app Strava, I'm sure you've all used it, it actually was exposing the location of secure military facilities because people in military installments were running and they couldn't leave the installment, but their paths were turning up on Strava, but nobody outside the installations could get into it. And so all of a sudden, here's this guy who's posting something on social media, Twitter. There's some heavy jogging activity on the beach around what looks like the reported CIA annex at Mogadishu airport. And they didn't even think about what they were doing. It was just that they were running with their fitness tracker watch on. So you have to be careful about that. Marketing is an obvious issue with security and location-based services. Location-based ads can trigger all kinds of things to come to you. And this can be something that's beneficial to you if you are looking for something or searching for a service. It also helps businesses, especially small businesses, get their feet on the ground. So here's an example where information security might actually help the little guy, proverbial little guy. So they're using a lot of predictive algorithms, a lot of machine learning, a lot of higher level decision trees and random forests and so forth to optimize the timing of ads and the placement of them and whose cell phone they go to. But let me talk about one area, and this is work that I have done with the Census Bureau. I've been working with them for about 6 years on the 2020 decennial census data collection. The response rates, what happens in April of the decennial census year, April 1st, is the census contacts everybody in the country. They do mailings out on the 1st of April, and there's a little form in there, and sometimes it's online, sometimes it's on paper, and it says, who lives there, and how old are you, and how much money do you make, and what race are you, races, mixed race, and so on and so forth. And it's a short form. It's like 10, 12 questions. But Wilbur Ross, who's the head of the census, was directed by the White House last year to insist that one of the questions that was added to the census was, are you a U.S. citizen? And everybody at the census, and a lot of people around the country, got very nervous because there is already mistrust of the government, and whether or not telling the U.S. government, the Census Bureau, I live here but I'm not a U.S. citizen, is going to cause ICE to come knocking at your door. And so everybody at the census, the statisticians and the geographers and the computer scientists and the GI scientists, were saying to the upper level management and to Wilbur Ross, this is a bad idea. It's still going through the courts, and I'm not sure what will happen, but in the meantime, the census staffers, who are really excellent statisticians, said, if we know we're going to get fewer responses on the census, let's use GIScience and administrative records from other databases, in order to figure out if somebody won't answer when they get contacted by the census. They won't open the door, won't pick up the phone, won't go out on the internet, won't have anything to do with it. Let's figure out if there's a way that we can help to count people accurately. Because not only does the census count turn into electoral college and voting for the president and so forth, it also is what gives the resources allocated from the federal government to states and cities for things like SNAP, food stamps, WIC, aid to women with children, all kinds of social welfare, Medicaid, Medicare services, access to health care. We need a new hospital. We need resources to this public school. All sorts of things come out of the 2020 census. So we know that people are going to not respond. And I'm saying we, this sounds like I've drunk the Kool-Aid, but I have been working with them for 6 years, and I think that the Census Bureau's intentions are right, and they are mandated by law not to release their data to other agencies in disaggregated form. And I think a lot of citizens don't believe that. We'll see what happens. So we've been working on using administrative records to reduce the costs of what is called NRFU, non-response follow-up, NRFU, NRFU, and maintain the quality of collection and reporting. So the administrative records draws from federal, state, third-party resources to populate this roster of 50 million addresses in the United States. We know that from statistics that about 30 million of these NRFU addresses are occupied, and another 20 are either vacant or non-existent. So the first strategy is to use machine learning to get the vacant and unoccupied ones out of the way. So you reduce your 50 million problems to 30 million problems. And then you take those 50 million and see if you can use administrative records. And here are some of the sources they use. If you have a social security number, you've given the government an address. And if that address matches one of the NRFUs, they can use your social security number to find out how many people are there. Or if you pay taxes, or if you're on Medicare and Medicaid, or if you're in the Indian Health Service, or if you're in the best race and Hispanic origin data. Or they find out from the U.S. Postal Service if anybody's delivering mail to you, and so on and so forth. And so these, in addition to MLS, the multiple listing surface real estate, and also the other census that's collected, the ACS, American Community Survey, and they're trying to generate these simulated records and then use statistical methods to test the quality and see if they can help people who are understandably afraid to answer the door. So, in summary, okay. GIScience is just great. Come down. We're over in Guggenheim. We're having fun. But there's a lot of things it can do better. And there's two aspects of research that are going on that are places where GIScience could really start to refine its methods. The first is methods that are emerging, being actively worked on. One is working with time. GIScience works really well with space, and they are starting to work well with time. And I'm going to give you an example of a moving objects research that's really some very cool stuff that's going on in Minnesota. And the other thing that GIScience should do, when I'm working with machine learning or decision trees or random forest, I'm working in RStudio. I'm not in a place where I can do mapping and graphing and have all that coordinate geometry infrastructure that GIScience provides. And that's a real pain in the neck. So adding something with machine learning, and both of these are emerging. So very quickly, I'll just show you. This is the work from Somaya Dodge at the University of Minnesota. This is actually an animation, and you can go out to YouTube and check this out. It's pretty neat. This is adult albatrosses that are foraging for they're making foraging trips to and from the coast of South America during the breeding season. And the way that Somi Dodge is tracking these is with GPS. So here we go. There's some GPS and obviously some remote sensing. But then she looks at the primary productivity of the foraging grounds and the wind speed and the flying speed and the tailwind to actually track where these birds are. So people are working on moving things, things that move over time. The other thing that changes over time is something that doesn't change position, but it might grow, like San Francisco, Washington, D.C., Phoenix. Yeah. The other example is machine learning, and I pulled this morning from the Esri website. So Esri, the makers of ArcGIS, which is sort of the Cadillac of the software GIS, they're doing some work with machine learning and GIS to predict where are the places most likely to have traffic accidents. under certain conditions. So the GIS data that they use is the weather, the time of day, the speed limit, the proximity to intersections. How's the road? Is it paved? Is it gravel? Is it plowed? Is it salted? So on and so forth. So the machine learning, what they're doing is they train a characterization of the road network for potential problems, and then once it's trained, they give the program scenarios. Like, what if it snows during rush hour, for example? What happens if there's a major accident in the mousetrap, where 70 and 270 and all the roads in Denver come together? So they are working with it, and a lot of researchers are working with it. We are not doing much with this kind of traffic work over in Guggenheim, but if you're all doing network stuff, like I said, come on down, we'd love to talk. And the other area, what can GIScience do better, is the stuff that's not really ready for prime time. We're very good at mapping. We do a lot of work with projections and coordinates, but we do not do work with dynamic visualization, animations, the stuff that Samaya Dodge is doing. She is doing her own work in Java, JavaScript, and so forth, and immersive vermal that could be used for, immersing yourself in a toxic environment that's very difficult to go to personally, but you could create immersive virtual reality models and use it as a research mechanism to go to a place virtually and stay safe. You could also use it as a pedagogic support tool, and none of that work is really going on yet in GIScience. The other issue is real-time monitoring of weather data, storm data, flood data, and so forth. We have a weather station on top of our building over in Guggenheim, and so we get real-time data for Guggenheim, right? But that's not going to tell me what's going on down in Denver. It's only going to tell me what's going on main campus. There are other kinds of data models, network data models, for example. The ones in GIScience are actually pretty crude right now. Ontologies, semantic data models that actually allow you to work and model relationships between concepts. Those kinds of data models are certainly available, the RDP triples and so on and so forth, and people are working with them, but they're not working with them within the framework of a GIS, within that infrastructure that they have all of that access to working with spatial data. So now you know everything there is about technology and policy and security in GIS. And we're about 3 minutes to 5, but I'd be happy to answer any questions you might have.
So let's thank our speaker, please.
Oh. I saw one hand. Yeah.
Sure, yeah. One in the IT world, one thing that we're looking at are Wi-Fi beacons to figure out location within a facility. And the idea is that you could use that in an IO psychology sense to understand linger time in break room and cubes and the impact on employee performance. How would something like that be related to what you're doing?
There's a very, very well-known GI scientist named Raymond Ng, NG, he's Vietnamese, and he was using streaming video and GIScience and some of this tracking the cameras in lobbies of skyscrapers to track paths through the lobby of this building. So, if somebody comes into this room through that door and they go right along here and they go out, or they come in and they sit here for a while and leave, but if somebody were to come in here at like 5 in the afternoon and still be here at 10 o'clock at night, you've got an outlier. So what he was doing with the GIScience work and this video and streaming and so forth was trying to figure out outliers that would tell the building security how to track problem people. Or if somebody comes into the lobby and gets sick, they faint or something like that, how can you go and help them? That's probably the best example I can think of. He's done some really neat work.
Thank you.
Yeah.
Oh, another question?
Yeah.
Do you know of any research that's been done currently with like very localized spatial data that's gathered from actual Wi-Fi signals that are being bounced around through the air? For example, mapping the actual people in a room based on how the Wi-Fi data in the room is bouncing off?
Like people talking to each other on their texting?
No, just the actual Wi-Fi signals.
Oh, no, I don't. What an interesting problem.
I just wondered, I had heard talk about it from one of the other professors, so I was wondering if.
Oh,
there was
yeah.
any-
No, I'm not aware of that, but it sounds really,
Yeah, it seems really interesting to me too, so.
yeah. I have to tell you, I love science. I mean, it's like there is no end to the stuff that's going on that's so impossibly cool, and not nearly enough minutes in the day to look at it. That's a great idea.
So given your data sets that you're looking at, I don't see very much need for security or cybersecurity associated with the data sets. So did I miss that?
I have not worked much with data that requires cybersecurity, but people do. I'm leaning towards examples of medical geography where people are working with people who have, I don't know, human papillomavirus or AIDS, something like that, but that's not really cybersecurity yet. So cybersecurity would have to do with looking at the spatial distribution of people who are tracking other people. Vehicle navigation might have something to do with, and there's a lot of work that's going on in Ohio State. Harvey Miller does quite a bit of work with that. There's a lot of work with tracking wildlife with GPS collars along like the Appalachian Trail and the Colorado Trail. That's actually going on in eBio, evolutionary biology and ecology, more than in geography because they're interested in habitat degradation. Those are just some examples. But I don't actually know of anybody in our department in geography who's working with the cybersecurity. Yeah. And I think the reason for that is not that it's not interesting to us, it's that we are not as knowledgeable about that technology as someone in engineering might be. And so there's some common ground for collaboration. Because we could help you with the spatial distribution and the routing and the tracking, but we probably don't have the wherewithal to know how to monitor the cybersecurity, just like the Wi-Fi. Yeah, another great example. Yeah.
So, Frank, did you have a question?
Question, put some time in Bayesian approach to defining probabilities and wondering what extent that's built into the way you use the information you have to build into your statistical models.
Yep.
Is that being done extensively?
We have started working pretty extensively with the Bayesian probabilities, not just within GIS, but political geographers are doing a lot of work with war conflict and uncommon events and using Bayesian modeling to support that work. So that's actually an emerging area that is really starting to take up a lot of interest in geography.
It just seems to me that you've got all kinds of sources of information. You'd like to have a systematic way of building them, how to use it.
That's right. And, you know, I think if you work with data mining, for example, the old term for machine learning and so forth, and classification, those Bayesian models can help you a lot in looking at distributions. They're not all Gaussian, and those Bayesian distributions, yeah, you probably know that. Yep. Yep. Yeah, good point. Good point.
So it's after 5. Let's thank our speaker one more time, please.
Thank you.
And thank you all for coming.